So I think we need to memorize amps. Amps is how many coulombs flow per second. Now, coulombs is a measure of charge, which we don't need to worry about what it exactly means, but we want to know how much charge flows per second. And this is not in your equations page. And you won't see it in more than one problem, but if you want to get that problem right, it's probably good to memorize. So an amp is a coulomb per second. Now, before I said if we have a problem of electricity and time, we would use this equation, but it's not going to really work for us now. Here we have amps, which will remind you that it's current. And again, current is just like water flowing. If you want to know water flowing, you want to know how much is flowing per given amount of time. And you have right below it coulombs and seconds. So I suppose you don't have to memorize it in the sense that if you know this is coulombs and this is seconds, then I is going to equal coulombs over seconds. So let's see, what we're given is 0.8 amps. So 0.8 amps is 0.8 coulombs per second. Now this is going to flow for 30 minutes. Well, I need to match it to seconds. So 30 minutes, well, of course 60 seconds in a minute. So 30 times 60 gets me to my units. And then now my seconds cancel out. So I'm left now with coulombs. Well, from coulombs, I can go to my equations page. And I know Faraday's constant is telling me there's 96,485 coulombs in 1 mole of electrons. And finally, I'm looking for the molar mass. Well, I suppose I should say there's 1 mole of electrons in 1 mole of silver. And then I could do molar mass. And so that will get me to here. All right, so what I have to do, I'm looking at another non-standard solution. I have 2 molarities of 1 molar and 1 molar. That's a standard solution. But they're telling me that my voltage is different than what I expect. It's greater than what I expect. Now I see that my magnesium is going to lose electrons. And so I need to understand that this reaction, as stated, this is again the reduction potential. They always give the reduction potential, never the oxidation potential. And so since my reaction is going this way, my electrons are flowing this way, that means magnesium is losing electrons, and so this would be flipped. And that means this reaction, this equation is good as is. So what I'm shown is that since my voltage is higher than it should be, that means either I have extra reactants, which Le Chatelier, if I have extra reactants, my voltage will increase. My reaction will happen faster, so to speak. And so if I look at silver plus ion, that is a reactant. So if I increase the concentration of my silver, that's going to increase my reactant, which Le Chatelier, it's going to make the voltage increase. So we're saying magnesium is going to stay the same, silver's increased. Q, that's our reaction quotient, product versus reactance. And so my Q is less than 1. That's telling me that my reactants are, I have more reactants than products. And that goes along with what I said. Extra Ag plus, that's a reactant. That's going to make my Q less than 1 because it's increasing the denominator. Similar problem here in that we're going to change the concentration to make it non-standard. So if we normally expect a 2.71 voltage and we want to figure out how do we get less than that, we're either going to increase products or we're going to decrease reactants. And so you see our solution here, we're going to decrease our reactants. So again, if we decrease this, Le Chatelier says our reaction wants to go in the reverse, or in essence, it wants to slow it down. And so Q is greater than 1 because, again, in my fraction, if my fraction is Q is product over reactant, if I decrease this, it's going to make my Q larger. So decreasing reactant makes this fraction larger, makes it greater than 1, slows down my reaction. So here we have a solution, an aqueous solution. We don't care about the nitrates. And so if I crisscross this, I derive the charge as 2 plus. And I'm going from a copper of no charge to copper 2. So that means it must have lost negativity. It's lost 2 electrons. So that matches to that. If I'm losing electrons, I'm oxidizing, or it's being oxidized. So that works with that. My silver, likewise, nitrate has a charge of 1. That means silver has a charge of 1. And so we go from a positive to neutral. It must have gained an electron to lose its positivity. If it gained an electron, it is reduced. And so that makes sense there. So here we're given our total cell potential. I'm given 1/2 reaction and asked to find the other one. So this is at 0.8. I know the whole thing is 2.46. And so I'm looking to find this. And so 2.46 minus 0.8 will tell me this is we know it has to be negative 1.66 as opposed to 3.26 because here they tell us this half reaction. This is reduced. And so whatever is reduced has to have a larger voltage than whatever is oxidized. So that's why we know the oxidized thing has to be negative 1.66 as opposed to 3.26. A lot of information in this one. It helps to think about reduction potential just like a physical thing. If I see something way up high and say that has a lot of potential energy, well, the farther it has to fall, the more potential energy it has. So that's kind of analogous to this. So I see if I have my stated things of zinc and silver, you can just visually notice my change, my difference between my two reduction potentials, pretty large. If I then replace it with lead, I see the difference between those is much smaller. So it has, analogously speaking, not as far to fall. And so that aligns with our answer for C. This question seems a little bit random. What you need to know is that distilled water does not conduct anything. And something that does not conduct anything is going to make poor use. It's going to be used poorly in a battery. All right, whatever has the largest value, not absolute value, but the largest value is going to be reduced. So this one's going to be reduced because -1 is larger than -2. So that's going to be reduced. That means this is going to be oxidized. And so since this is going to be oxidized and it's as written, it's reduced, we have to flip this one. So we would flip this one. We need 6 electrons going in, 6 electrons going out. So we'd multiply this whole equation by 3 and this whole equation by 2. Now when we multiply the equations, it does not affect the voltage. So we're going to flip this equation. We're going to have our common multiple of 6. We add those together and we get our equation. As far as the voltage goes, again, if we just think about it as how far away from each other they are on the number line, that's how we get our 0.9. And since it's favorable, we know it has to be positive. This one's just a definition. My equilibrium is very large. That means products are favored over reactants. So a lot of products, very little reactants. If a reaction is favored, by definition, E is positive and Gibbs, G, is negative. So if I have 1 mole of nickel metal, and from this I see my charge for nickel is 2+. And so 1 mole produces 2 moles of electrons. And I suppose I'm looking for how many it's going to gain, so I should leave off the charge. And that's what it's looking for, not nickel plus. So 2 moles of electrons. Now they tell me this right here. So 1 mole of electrons is going to contain 6 times 10 to the 23rd electrons, which is equal to 96,500 coulombs. And we're going at 1 amp. And 1 amp is 1 coulomb per second. And I'll just flip that upside down so I match up my coulomb units. This is a time question, so if you can, we're going to use the I equals Q over T, just by definition. So we're looking for the lowest cell potential. So a large difference in molarity would signify a low cell potential. And then again, we're looking at our concentration of zinc 2+. we're going to increase that. And so if we increase that, Le Chatelier says we're going the opposite direction, or in essence, we're slowing this down or lowering voltage. And just to compound that, we're actually lowering our Fe2+, which has the same effect. So both of those things are going to lower the voltage, more so than these others.